So today we're going to learn how do we predict the products for double replacement reactions. So first we just have to understand what double replacement reactions are. So these reactions, they just involve the exchange of cations between two compounds. And then do you remember how last week we were writing generic formulas with like A and B and C? Okay. So let's add that. I don't have a ton of space, so I'm going to add at the bottom. So what a double replacement reaction would look like, you would start with two compounds. So we'll say you start with AB and CD. Okay. And so in these reactions, the two cations switch places, or those are the two elements that are going to come first. Okay, so A and C are just going to switch places. So then for products, you'll have CB plus AD. Okay. So I would recommend writing that one down. That might also help make sense of what do the words mean. And then when we have these type of reactions, we have two scenarios that can take place. Okay. So just because we mix two chemicals together, does that mean they have to react? No. Okay. So there's always the chance that there's going to be no reaction, and we just say RXN to abbreviate reaction. Okay. And we'll do examples today. I'll show you like how do you know if it's going to be a no reaction. Or the other scenario is like, yep, they can make something new and yes, a chemical reaction occurs. Okay. And again, we'll do some examples today and I'll show you how do we know if we'll have a chemical reaction or a no reaction. All right, so today we'll learn how do we like look at reactions on paper and know if a chemical reaction is going to take place. But then we'll also do lots of reactions today like in class. So in real life, how do we know if chemical reactions are happening? So one, we can see a gas being produced. Or let's say the gas is colorless. What else would you see that would like tell you a gas is being made? Bubbles. Okay, so gas produced or sort of bubbles. Okay. You might make something called a precipitate. Okay, so a precipitate is a solid. So like if you mix two liquids together and you make a solid, we call that solid the precipitate. Or when we do double replacement reactions, we start with two ionic compounds. So if you start with two ionics and you make a molecular compound as a product, such as water, then like, yes, you're also getting a chemical reaction because you're making something new. Okay, so then let's say we're looking at a reaction on paper. We're not going to see if it like bubbles or makes a gas or makes a precipitate or makes water. Water we'll see. So how do we know? So how do we know if a double replacement reaction is going to take place? We're going to use something called solubility rules. Okay. So last week you got this activity series. So go ahead and look at the back side. Okay, so if you look at this chart, so we have the solubility rules chart. So if you look, the first column, this time it actually starts with anions or the negative charged one. Okay. Anions are the ones that come second in the compound. Okay. And then you see next is like plus the positive ions or the cations. Okay. And then it gives you its solubility. So on your notes, let's make a little key of what solubility actually means. So if something is soluble, okay, it means it's going to be aqueous. And aqueous, we're just going to write AQ for short, and I'll show you like when we write that. Okay. And then if we want to add to your notes, aqueous just means it dissolves in water. So a good example of aqueous is like making Kool-Aid. How many of you have made Kool-Aid at some point in your life? Okay. So when you put the Kool-Aid powder in the water, it dissolves. You made an aqueous solution. Okay. So if it's soluble, it means it dissolves or it makes this aqueous substance. And what we're going to actually write is this little AQ for aqueous. And then if you keep looking at solubilities in the chart, you see that they can be soluble, or what's the other option? Okay, you'll see it either says low solubility or insoluble. That means you make a precipitate. Which is just a solid. So you take two liquids and you made a solid. So what we write in parentheses is a little S to show that you made a solid. Okay. And we'll do a couple practice problems. I will show you like how we use these in those practice problems. Okay. So right now, our only goal is like really just understanding vocab. So soluble means aqueous, and we write AQ. Low solubility or insoluble means you're going to make a precipitate or solid, and we're going to write an S. So we're going to do a couple practice problems together, and then I'll have you try at least one on your own. Bless you. Okay. So go ahead and just copy down the reactants. So we have Na2S. Okay. And I'm going to put the little AQ, it's aqueous, plus CdNO3 And you'll notice a trend, our reactants are always going to be aqueous. Okay. All right, so now our goal is going to be determine, well, if we mix sodium sulfide and cadmium nitrate, well, what products do we actually make? So in a double replacement reaction, the cations are going to switch places. Okay? And the cations are going to be the first element in the compound. So if it helps for you to draw arrows, you can draw your arrows. So sodium and cadmium are going to switch spots. Okay. So that means sodium is going to move over here and it's going to bond to the nitrate. And then cadmium is going to move over here and it's going to bond to the sulfide. When we make our new formulas, we're going to keep on doing that crisscross rule every single time. Okay. So I'm going to start with cadmium and it's going to bond to the sulfide. Cadmium, it doesn't show up on your periodic table for charges. Okay. If you look, cadmium isn't on the list. So I'm just going to give you the charge today. Okay. So cadmium is just a +2 charge. Okay. And then it's going to swoop in over here. So it's going to bond to sulfide. And then what kind of charge does sulfide have? Good. Okay, -2. So then once you have your charges, what do you do? Okay. Crisscross, what do we get? Okay, and it's going to reduce down to, okay. So one of our products is going to be CDS. And then for our other product, nitrate is going to move, or sodium is going to move over here, and it's going to bond to the nitrate. So again, crisscross rule every time. Okay. What's the charge of sodium? Okay. So sodium has that +1 charge. And then where would you find nitrate's charge? Okay, on the back. So nitrate is NO3, and then what kind of charge does it get? Okay, -1. So once you do the crisscross rule, what do you get for that formula? Good. Okay, so we're going to NaNO3. Okay, so now before we balance, this is going to be a new step. So how do we know if a chemical reaction actually took place? Okay. So again, just because you mix two chemicals, does it mean they have to react? No. They don't have to. So how we know is we're going to use the solubility chart. Okay. And we're going to look up the solubility for each product. So let's start with cadmium sulfide first. Okay. If you look at your chart, the anion comes first, which is always the second part of the compound. So in this case, it's sulfide. Okay. So go down on your chart until you find sulfide. Okay, then we're going to move over to the cation. Do you see how the first row, it gives you like a whole list of elements that it could bond to? Is cadmium one of those that's listed? Okay. Nope, so you drop down to the next row. Do you see how now it's sulfide plus any other cation? Okay, so cadmium fits into that category, so we go over 1. So then what's its solubility? Okay, it's low or insoluble, which means these are going to make a solid in solution. So we're going to put a little S, like it's a little subscript, S in parentheses. So that means it's going to make a solid. Then we're going to do the same thing for sodium nitrate. So again, you start with the anion first. So use your chart and go down till you find nitrate. And then nitrate, does it matter what cation it's bonded to? Okay, so what's that solubility? Okay, soluble, which means it's going to dissolve in water. So what are we going to write? Okay, so we're going to put little AQ. Okay, so then because one of our products is a solid, it means yes, a chemical reaction actually is going to happen. So I'm just going to write yes. I'm going to say RXN for reaction. Okay, so because we made something solid, yes, we're going to see a chemical reaction. If I were to mix these two compounds, we're going to make something new. I'm going to see something change. Okay. And so then, yes, there is a chemical reaction. What's our final step? Okay, let's balance it. I would start with the nitrate because it's the hardest one. So how many nitrates are on the left side? 2. So what should we put over here?
2.
Okay, so I'm going to put a 2 in. And that now gives us how many sodiums?
2.
2, and how many are on the left side? 2. How many sulfurs?
1.
And how many sulfurs?
1.
Good. How many cadmiums?
1.
And how many cadmiums? 1. Good. Are we balanced?
Yes.
Good. Okay, let's check out our second example. NaCN plus H2SO4. So go ahead and copy down those reactants. Okay, so first step is we have to know which elements are trading places. So which elements do you think are going to like switch spots? Okay, so sodium and hydrogen, they're just going to swap places. So if it helps you to draw the arrow, feel free to draw the arrow. Okay. And then what are we going to do every time so we get the formulas for the products correct? Okay, crisscross. So hydrogen is going to come over here and bond to the cyanide. Okay, so I'm going to start there. So what kind of charge does hydrogen get?
+1.
Okay, so hydrogen's +1. Cyanide, where would you find the charge? Okay, it's on the back. And what is the charge of cyanide? Okay. So when you crisscross rule, what do you get for hydrogen cyanide?
Hydrogen 4 cyanide.
Hold on. Okay, so we should get HCN. And then for our second product, sodium is going to come over here and bond with sulfate. Okay. So what's sodium's charge? Okay. And then where would you find sulfate's charge? Okay, on the back. What is the charge of sulfate? So sulfate's -2. And then what do you do with those? Okay. All right. So then what do you get for your formula? Okay. So we get Na2SO4. Okay, so now our next step is our new step. What's our next step? Okay, solubility. So that's going to tell us if these chemicals actually react or not. Okay. So cyanide is the first anion. So go ahead and look at your chart. Do you see cyanide anywhere on that chart? No, right? Cyanide's not on the chart. So instead of the anion, now we're going to have to look at the cation. So look for hydrogen ion and make sure you're on the second column, the cation column. Okay, so do you see hydrogen ion? It's like second to the top, yes? Okay, so does it matter what it's bonding to? What's its solubility? Okay, soluble. So what are you going to write? Okay, soluble is AQ for aqueous. And then our next one is sodium sulfate. Okay, so find sulfate on the chart. And then is sodium one of those listed elements? Okay, so you got to go one row below. So any other cation, what's its solubility? Soluble, so where are you going to write? AQ. Okay, so when you have this scenario, do you see how both products are AQ? Okay, this is a no reaction. So you can just write no RXN for no reaction. So then if there's no reaction, do you need to take the time to balance it? No. That's why I save balancing for the end. Okay. And then let me show you just up here why it's a no reaction. Okay. So for you, you can like stop here in your paper, but I want you to watch up here why we would say no reaction. So the first one, sodium cyanide is aqueous. So that means in solution, it just breaks off into sodium ion and cyanide ion. And then again, H2SO4 is aqueous. So it's going to break off into hydrogen ion plus sulfate ion. And on the right side of the equation, we have HCN, which is aqueous. So it's going to break off into hydrogen ion plus cyanide ion. And then in sodium sulfite is aqueous, so we're going to get sodium ion and sulfate ion. So now let's compare the left side and the right side. So the left side, we have sodium with a 1 plus, sodium plus 1. Okay. We have cyanide ion, hydrogen ion, sulfate ion. Is there any difference between those two sides? Okay, do they look identical? Okay, so in these scenarios where everything is aqueous, there's literally nothing changes. Okay, so we say no reaction. If you were to mix these in real life, what would you expect to see? Nothing, right? Nothing's going to change. So go ahead and copy down these reactants. Okay, and then first step is just knowing which two elements are switching spots. Okay, calcium and hydrogen. So again, if you need to draw an arrow, just so you know, feel free to draw that arrow. Okay. So hydrogen's going to move over here and bond to hydroxide. So again, off to the side, I'm still doing the crisscross rule every time. Okay. What's the charge for hydrogen? Okay. And then where would you find hydroxide's charge? Okay, on the back. So if you find hydroxide, what's its charge? Okay, -1. So once you do the crisscross rule, what do you get? Okay, HOH, and what is HOH? Okay, it's the same thing as water. Okay, so HOH is water. In this case, I'm going to keep it as HOH, and I'll show you. It'll make balancing easier. But do we know that HOH is water? Okay. Then we'll do the same thing for our second product. Calcium is going to move over here and bond to the chlorine. So what's the charge of calcium?
2.
Okay, plus 2. And then what's the charge of chloride? -1. Okay, so when we crisscross, what do we get?
Calcium, chloride 2.
Good. Okay, so we get CaCl2. Okay, what's our next step? Okay, next step is solubility. So water doesn't fit into the solubilities chart. This is for ionic compounds. In water is molecular. Okay. However, what is water at room temp? Is it a solid, a liquid, or a gas? Okay, so we're gonna just put a little like lowercase l. I tend to do like a cursive L here. So it's a little liquid. So like a little lowercase l to show that it's gonna be a liquid. And then calcium chloride is ionic, so you're back to your solubility chart. Okay. So you try to find the solubility of calcium chloride on your own this time. All right, what are we finding for calcium chloride solubility? So go down to chloride. Is it one of these cations listed?
I did not see that.
Oh, that's okay. So it's soluble. So what are you going to write? Okay, AQ. For this one, since you made a liquid, Yes, there'll be a chemical reaction that takes place. Okay. And so then, since you did have a chemical reaction that takes place, what's your final step?
Balance.
Okay, balance. Okay, so there is a reason why I recommend keep water as HOH. Okay, do you see how you have OH on this side of the equation?
Yep.
Okay, I'm going to just put OH in parentheses. It doesn't need it, but I think it's going to help you visualize things better. Okay, so then I have OH on the left and I have OH on the right. So I'm going to balance those as one thing. And then do you see how you have hydrogen by itself now? Okay, I'm going to balance that to this hydrogen. Okay, you with me? Okay, how many OHs are on the left side?
2.
2. So what coefficient do you need? Okay, so I'm going to put a 2 here. Okay. But now, how many hydrogens do I have?
2.
2. So what do you have to put over here?
2.
Okay, that also gave me 2 chlorines. How many chlorines are on this side?
2.
2. How many calciums here?
1.
1. And how many over here?
1.
Good. Are we balanced?
Yep.
Good. Okay, I want you to try one on your own. Okay, so try BaCl2 plus K2CO3. Okay, and try as far as you can get by yourself. How far can you go without help? Okay, what's one of the first products you get? Okay, we get KCl. Okay. Let me just show the crisscross rule on this one. So potassium is just K by itself, and what kind of charge does it get?
+1.
Okay, +1. And then chlorine is just Cl, and what kind of charge does chlorine get?
-1.
Okay, -1. So if you crisscross, you end up with KCl. Okay. When I was walking by, I think some of you wanted to carry these subscripts over. Okay, don't carry them over. The only time you're going to carry a subscript over is if you look at the back of your naming chart. If it has a subscript like in that formula, then you carry it over. Okay. Yes. If it doesn't have a subscript, then you don't carry that over. Okay, you just get them from crisscross rule. And then what's your second product? Good. Okay, we get BaCO3. Again, let me show you the crisscross rule. Barium has a +2 charge. And then if you look at the back, carbonate is CO3. So if you look on here, like part of the formula is CO3, so that 3 does get carried over. It has a -2 charge. Are those +2 and -2 going to balance out?
Yes.
Okay, so it just becomes BaCO3. What's the solubility for KCl?
AQ.
Okay, it's aqueous, and then what about BaCO3?
S.
S, you make a solid. So, yes or no for chemical reaction?
Yes.
Good, yes. So then what's your last step?
2 balance.
Okay, balance. What do you have to do to balance this one?
You just have to put a 2 over the, or 2 before the potassium chloride.
Good. Okay, do y'all agree? Good. And then the last thing I want to point out, acid-base reactions. So when you mix an acid and a base, they're still a double replacement reaction. Okay. So you would treat them exactly the same as we have been treating. So just the cations switch places. And then your products, you're always going to make water, HOH, and then some sort of salt. It's not always going to be table salt, but it will be some sort of ionic compound. Okay. So if you see acid-base reaction, just treat it like a normal double replacement.